This last lecture for Chapter 21 is fairly short. I just want to concentrate on two topics, nuclear fission and nuclear fusion. And that is spelled wrong. Should just be one S there. Mainly concepts, one type of calculation to worry about, and that's actually where I'm going to start off with after I do a brief intro of what it means to undergo nuclear fission. And all we're talking about here is this is not this is something I'm going to look at here in a minute. 238 and 92 is its atomic number. You know, before what we did is we looked at it's not that, it's H. This isotope of uranium, uranium-238, undergoes this decay process. It's a beta decay. It's the thorium product here. When we talked about the radioactive equations from the first lecture, which is the bulk of what we've seen up to this point, we had this kind of decay process. It just happened on its own. There's an inherent instability in all nuclei that have an atomic number of 84 or greater. And so over time it's going to disintegrate and kick off this radiation and another isotope, which this one is radioactive as well because it has an atomic number of 90, which is again above 84. In the very first slide of the second lecture, we did a bombardment reaction, and that's what a nuclear fission. That's how you start off a nuclear fission reaction, is a bombardment reaction. Then we're taking a large isotope of uranium, in this case 235, and we're striking it with a neutron, a bombardment reaction. And notice that there's quite a couple of pathways it can take in terms of falling apart. And in both cases, we kick off a greater number of neutrons than what we actually started with. And then these neutrons can then go on and cause more of these bombardment reactions to occur. And we'll mention what that's all about here in a minute. But the main thing I want to talk about is the energy change that occurs, or the energy that's released during this kind of bombardment reaction. If you were to measure the mass of what you begin with and then the mass of what you end with, there's a mass difference. When you first look at it, it almost appears like there's the law of conservation of mass have been violated, but that's not the case, because the mass change from this side to that side, that amount of mass is actually converted into energy, and it's a very famous equation from Einstein. This is from 1907, and what it's telling me is that whatever amount of mass has been lost during this nuclear reaction, it's going to release a certain amount of energy into the environment. Let's do one of these calculations, not on this guy. This is a bit long-winded, and actually, I'm scaling back the kind of calculation that you have to do here. I'll just tell you that right now. I just want you to use the equation. I want you to appreciate how much energy can actually be released through one of these reactions. That's why using this type of technology to generate electricity in a nuclear power plant is not a crazy idea, because you generate a lot of energy for just a very small amount of mass. Now it's what's left over at the end that's the big problem, but anyway, that's not for me to solve here. And I don't want to do a bombardment reaction for the first example. I actually want to do this reaction, and the book breaks down the mass of the product side and the reactant side that you can take a look at for this equation. I'm just going to go and tell you that there's a mass change. It's very small, actually. For 1 mole of this stuff, there's only 4.6 milligrams that actually is lost. It's actually, this is converted over to energy, and we calculate that from E equals mc squared. and I'll give you this information. I'll give you the mass. I'm not going to have you go through and calculate all the masses there. The one thing to keep in mind is that this needs to be in kilograms, because the unit of energy is going to be joules coming off of this. Joules is a derived unit, and within that derived unit is kilograms, meters, and seconds. And so make sure that you've converted this to kilograms, and it will look like this: 10 to the minus 6 kilograms. And then C is just the speed of light, which, if you don't know it, I'll give that to you. Meters per second squared. And when you calculate this, 4.14 times 10 to the plus 11 joules are released per mole of uranium when it undergoes this particular decay process. So a very small mass change generates a huge amount of energy. This is I'm just taking this from the book. This is 50,000 times more energy than what is generated from the combustion of methane, natural gas. That's an amazing amount. That's why it's so tempting to use this in a nuclear power plant and to generate this amount of heat with conventional hydrocarbons. It takes 50,000 times as much methane to generate the same amount of heat, and that heat would be used to boil water, turn a turbine. We'll look at the power plant here in a minute or so. But if you're trying to figure out a rationale about why humans have chosen to use a nuclear power plant to generate electricity, even with all the nasty waste that is generated and the possible dangers with it, well, this is why, because it's such a hugely exothermic reaction. The other type of calculation here is really just going the other way. You're given the amount of heat for 1 mole of this undergoing a positron emission, and again, this is, if you've made it this far through the course, manipulating E equals mc squared and plugging these values in, I don't think will be very challenging for you. So, and we'll just go ahead and add the per mole there, and that's 3.00 times 10 to the 8 meters per second. And so the mass change from one side to the other is a very small amount, just like before, and minus 6 kilograms. So 3.2 milligrams of mass is lost. It's not, it's not a violation of the conservation of mass or a violation of conservation of energy. Everything's still accounted for. There's not, some amount of that substance that just disappears into the ether, never to be seen before or detected. So all the equation is doing is relating mass and energy. It's telling us interchangeable. And, that's been we take advantage of that for good and bad, for, nuclear bombs and power plants as well. So, what's happening? How does this actually occur? It's one thing to get a single reaction occurs a certain amount of heat, but then, again, appreciate the fact that a bunch of neutrons are just being kicked off here. And so, what's going to happen is that, you get something called a chain reaction, and if there's enough neutrons there, you get something called critical mass, where the reaction gets out of hand is what happens. I was about to use, I guess you could use the word spontaneous, yes. It goes without any kind of intervention, but it gets out of hand. It would, blow up on you, a meltdown kind of thing. So initially, if let's say the density of the material isn't terribly great, you get the one neutron coming in, smacking into your uranium. You kick off a couple neutrons, and it may cause a few more uranium molecules or atoms to disintegrate. Okay, this would be subcritical mass example. Chain reaction stops. If you pack them in more tightly here, what happens, that one neutron, it triggers all of these additional events, and everything just sort of gets out of hand on you. And so you can't stop this without some kind of intervention. And this would be an example of something at critical mass, and the chain reaction continues. So this chain reaction is indicated by the neutrons continually bombarding additional uranium atoms. Now this chain reaction, if you can control it, well, you can do pretty neat things like generating electricity here. So in this portion of the diagram, you have the reactor core. This is where your radioactive material is. This is where the nuclear chain reaction is occurring inside these control rods here. The heat that is generated from the control rods heat up who knows, maybe antifreeze. It's probably more sophisticated than that, but it transfers the heat to water now, generates steam, and then that turns a turbine, which then sends out electricity through the wire, and then the water is recycled through the process. Now, as long as there's no leak here, there should be no reason why this water that's used for the steam production is radioactive, and so it shouldn't be that big of a deal to pump it back into the river or to the lake that it's being used. And then one other thing to note about modern, especially nuclear power plants built in the West. I'm thinking of the United Kingdom, France, the U.S., Japan, modern countries in the context of mid 20th century kind of thinking here, or labels. There's a certain design that you see for these nuclear power plants. Two things that pop in my mind very quickly here is one, there's a lot of concrete around a power plant in France and in the United States. The reason why I keep mentioning France is because if I'm not mistaken, that country is the one that generates the greatest percentage of their electricity through a nuclear reaction. I think it's somewhere in the 70% range. 70% of their electricity, or maybe more, is generated using nuclear power plants. And when my wife and I traveled to France a few years ago, we did see quite a few nuclear power plants as we made our loop around that country. One reason why the power plants in the West aren't terribly dangerous to some degrees is we have the concrete around the reactor core, and that's designed to stop any extra radiation that escapes from the reactor core. And I'm not sure that the Chernobyl event that occurred in I guess the late 80s or so over in I guess it's in the Ukraine, I believe, Soviet satellite at that time. And they may have had a reactor core cover like this, but the big problem with Chernobyl were these control rods that you see in the diagram here. Remember what I said, the chain reaction is occurring in this reactor core, and what is needed for the chain reaction? What is needed for that critical mass to occur? Well, you need a bunch of neutrons being kicked off. That's where the control rods come into play. If the reaction starts getting out of control, then they drop the control rods, and the control rods absorb the neutrons, is essentially what we're seeing here. So control rods absorb the excess neutrons, and it actually shut down the chain reaction. Now, graphite is good at doing that. Okay, so graphite control rods can absorb neutrons really well. Well, one problem with just pure graphite is that graphite will burn. What is graphite? Graphite's just carbon. Carbon is hydrocarbons. They're very good at burning, undergoing a combustion reaction. The control rods at the Chernobyl plant, my understanding, were more of this design, where it's maybe pure graphite, possibly. Reaction gets out of hand, a lot of heat is generated. You may be absorbing, some of the neutrons, trying to slow down the chain reaction, but at the same time, this stuff is heating up really hot, and it catches fire. Now it no longer is absorbing neutrons. The reaction gets out of hand and you get the explosion. Now in Western design for nuclear power plants, there's certain elements that are certain chemicals that are used to spike the control rods that keep them from burning. I think cobalt and chrome possibly are two of them. Don't quote me on that, but there's extra little components that are incorporated into the control rod to where it takes a lot more heat before they break down. And so you don't have that trouble that you had in Chernobyl in terms of the thing taking off on you. So that's probably the biggest difference, because if this thing goes critical and does a meltdown, I don't know if it matters how much concrete is around it. To tell you the truth, I mean, it's going to help, but if it really takes off, it's not going to matter. As long as the control rods are dropped, if you drop the control rods completely in there and they stay intact, which occurs in Western style reactors, and you stop the neutrons and the chain reaction stops. Now, in some uses of the more unfortunate uses of nuclear fission, is the atomic weapon. So this is a little schematic diagram of the atomic bomb. The two bombs that have been used in warfare in 1945 in Hiroshima and Nagasaki was should be fission there. That's a big problem. But it was a fission bomb where the uranium was breaking apart, and they didn't care. They don't want that reaction under control. They want it to take off. And so what you get is the mushroom cloud. Now, to get one of these atomic weapons to actually reach that critical mass is that you have conventional chemical explosive that is on one end of the bomb. And then my understanding is that when it's detonated, that the two portions of the uranium slam together and then the explosion is set off, or maybe vice versa. And that pressure that builds up in that kind of system then sends the uranium into the chain reaction, and you get that critical mass and you get the explosion. Now, the particular bomb that used these fission bombs, they are of course very dangerous, but actually you get more heat and energy and radioactive fallout, if you will. It's more dangerous to use the process known as fusion, something called the hydrogen bomb, which was developed in the 50s. It was after World War II, and it doesn't quite generate a mushroom cloud. It looks more like a bubble that's formed that travels across the land as this thing sets off. And what's happening here, and you see just a simple reaction for a fusion reaction. You have deuterium, which is one isotope of hydrogen, and then this is tritium, a heavier isotope of hydrogen. If you put this under high pressure and high temperature, you can get the thing to fuse together, and there's an enormous amount of heat that is given off during this reaction. To set off a hydrogen bomb, which is fusing together, I don't know the chemicals that they put together here, but to fuse together the compounds or the elements in your bomb, they actually use a traditional fission bomb to generate the heat and the pressure required to get this kind of reaction to occur. So, in some ways, the two bombs that were dropped over Hiroshima and Nagasaki in 1945 were fairly low-tech stuff compared to what's in the arsenals these days. If my understanding is correct, the nuclear arsenal that Russia and their former satellites and the U.S. and probably France and Britain in our arsenal now are mainly, I believe, these fusion weapons. These days the old style fission bombs are developed and tested by smaller countries such as, and smaller I mean by like economic standards, not physical, geographical size, economics, like North Korea. In 2006, the bomb that they tested was a fission type bomb. But the fusion bomb, okay, yeah, it's pretty nasty, but all it's doing, it's the same type of chemistry, if you will, nuclear chemistry, that is what's occurring in the sun, releasing all that heat. Now, the one thing about the fission, well, there's, I guess, a couple of things. One thing is you get non-radioactive products once it's all said and done. If you look at that, that's helium. That is not radioactive. It's very benign. It's not like you get some a bunch of plutonium or thorium that you have to deal with for the next 10,000 years. So that's a big positive for it, and you create a lot of energy from it. But the problem is, currently anyway, is that you're really putting in more, like to get a controlled reaction to where you can use it to generate energy and electricity for the use by mankind as a cheap, clean energy source. Well, you're essentially, currently, my understanding, you put more energy into it than what you actually get out. That's no use, right? The little apparatus that the tokamak test reactor that is shown in the figures from the book, yeah, it can use magnetic fields to generate the heat required to drive these types of reactions forward, but you can only reach 3 million Kelvin at this point. That's really hot, but it's not anywhere near the 40 million Kelvin that's required, I guess, a sustainable type of fusion reaction. And every few years or so you hear some group of researchers have developed cold fusion. The term always bugs me because it makes scientists look silly sometimes. But anyway, when you see cold fusion, I don't know if you would necessarily say that they think they've done fusion at room temperature. But honestly, I haven't really investigated the process, because every time this thing splashes across the news page, the headlines, it quickly dies down. If someone actually develops a method that generates a lot of clean energy very cheaply, you'll know about it. So, but the cold fusion, what it is that it's probably the researcher working with some system, and it spiked on the energy scale in terms of what they're generating. It's not like a meltdown or anything, but it's an unusual amount of energy for what they're expecting, is my guess. But like I said, if these things are for real, you're going to hear about it, because we need a nice, if we had a nice, clean, cheap energy source, many of the world's problems would be solved pretty well. I guess that's one reason why this is talked about, is because if this does ever happen, that's really great. Anyway, you can see in this last presentation one calculation using Einstein's famous equation, and then just a couple concepts about fission, fusion, and then I guess of all the concepts, I spent most of the time on the nuclear reactor here, and then this concept of what is a chain reaction, what is critical mass. Okay, so that summarizes it right there. Thanks.